they couldn't really be explained in the context of what physics was known at the time, and we've finally gotten to the point now where we can use the quantum mechanics we've learned so far to explain these bright line spectra. At least some of them, perhaps. This is the spectrum of hydrogen, this is the spectrum of mercury, this is the spectrum of neon, and this is xenon. So, 4 gases, and we'll be able to explain successfully the most simple gas possible, hydrogen. Our discussion of the time-independent Schrodinger equation in 3D, separated in spherical coordinates as appropriate for the spherically symmetric potential of a charged particle orbiting a nucleus, gave us psi with 3 quantum numbers n, l, and m. I'm not going to reproduce the long, complicated expression for what these are, but you know the radial part is given by the associated Laguerre polynomials, and the angular part is given by the spherical harmonics. As we went through the solution of the time-independent Schrodinger equation, we introduced a variety of constants, and then requirements, in particular for periodicity in the phi solution, the convergence and well-behavedness of the angular solutions, and convergence and well-behavedness of the radial solutions, gave us quantization conditions that we used to construct these n, l, and m. The constants that we got, for instance, we defined a k squared that was given by a 2me over h bar squared. That should look familiar. We found out that that constant had to be given by 1 over some a squared, some radius squared, times an n squared quantum number. This a value, the Bohr radius, is about half an angstrom. And the energies that we got, after unwinding all of those definitions that we made, look something like this. You have the energy of the nth energy level, the nth stationary state, the stationary state with n as the quantum number, is given by this constant times 1 over n squared. And that constant should look familiar. It's minus 13.6, or it's 13.6 electron volts, with a minus sign out front, signifying that these are bound states. Their energy is less than the energy of a free particle. So minus 13.6 electron volts over n squared, those are the energy levels of our stationary states. Our stationary states are not going to be stationary in reality because atoms bump into each other and atoms interact in random ways that we haven't described the physics of yet. But suffice it to say, perhaps, that these energies are not going to remain forever fixed. If I prepare an atom in, say, the n equals 3, a quantum state with n equals 3, it's not going to stay there forever. After a while, it will lose that energy, and when it does, it will emit a photon. The changes in energy that take place are energy carried off by the photon. So we would say, for instance, that if we had, say, n equals 3 goes to n equals 2, there's a change in energy here, and we would say the atom has emitted a photon. Correspondingly, if you have an atom in state n equals 2 and it's excited up to state n equals 3 by an electromagnetic field surrounding the atom, we would say this atom has absorbed a photon. This absorption and emission of photons, photon here is our shorthand term for a particle of light, or quanta of light, perhaps I should say quantum of light, is really the crux of the matter here. All of our experiments that motivated quantum mechanics had somehow to do with the interaction of light and matter. With our treatment of the hydrogen atom, we now have descriptions of how we can calculate changes in energy on the matter side. We haven't really said anything about the photon side, and unfortunately for that we'll need relativistic quantum mechanics, which is a topic for another course. But at any rate, you know that light is going to be emitted and absorbed in quanta, and the energies of those quanta are going to be given by the changes in energy of the thing that we can calculate, the thing that happens on the atomic side. So these stationary states are not going to be all that stationary, and by plugging in numbers for initial and final energy levels, you can calculate out what the energy of the photon would be, what the change in energy of the atom would be. These transitions have names, and this is a very standard visualization of what those energies might look like. The y-axis here is an energy scale, and it has 0 at the top. Anything with energies higher than 0 is not a bound state. The thick horizontal lines here represent the energies of the nth energy level. Here's n equals 1, the lowest energy level, n equals 2, 3, 4, 5, 6, 7, etc., up to infinity, where the bound state isn't really bound anymore. It has essentially zero energy. The transitions that are possible, for instance, if we're looking at the emission of light by a hydrogen atom, the atom is going to start in a higher energy level and drop down to a lower energy level. When it does so from an energy level 2, 3, 4, 5, 6, etc. up to infinity, all the way down to the ground state, n equals 1, we call that a Lyman line. The emission in the spectroscopic context has a particular pattern of energies that were first examined by, well, Lyman, and the lines are named after him. Transitions that start with 3, 4, 5, 6, etc. go up to infinity and drop down to the second energy level are called Balmer lines. Likewise, end state lines with n equals 3 are Paschen lines. There are also bracket lines. You don't hear very much about them. Even less common are the Pfund lines and the Humphrey lines, which you can imagine have a final state of energy 5 and energy 6. So these transitions are the sorts of things that you would expect from the energy structure that we calculated as a result of the time-independent Schrodinger equation with a 1 over r potential. The transition wavelengths can be calculated pretty simply. What we have here is an energy that we can calculate, and we know the energy of the photon is going to be given by Planck's constant times the speed of light, let's say Planck's constant times the frequency, or alternatively Planck's constant times the speed of light divided by the wavelength. Note that this is Planck's constant, not h bar, the version of the reduced Planck's constant that we've been using so far. So when you actually go out to calculate these things, you can calculate wavelengths easily by using the expression we had for the energy change by the atom, using that as the energy of the photon. The symbol for photon is gamma, typically, and solving for the wavelength. Doing so, you end up with this sort of thing, and this is a logarithmic scale now, 100 nanometer wavelength, 1000 nanometer wavelength, 10,000 nanometer wavelengths, and these things fall in very specific patterns. The Lyman series, which ended with n equals 1 as the final state, so this is a 2 to 1 transition, the longest wavelength Lyman line. This would be a 3 to 1, 4 to 1, 5 to 1, etc., all the way up to infinity to 1. Likewise for the Balmer lines. 3 to 2, 4 to 2, 5 to 2, 6 to 2, 7 to 2, etc., up to infinity to 2. Same for the Paschen series, and the bracket series, and the Pfund series, and the, I forgot his name already, the Humphrey series. They all have these nice patterns, and they all overlap, and if what you're looking at is the visible spectrum of hydrogen, you're looking at the Balmer lines. There are probably other lines that are visible if you look at a, quote, hydrogen gas, unquote, source being excited by a gas discharge, high voltage, for instance. Those are likely due to impurities. And if you think about the hydrogen atom, well, that's going to behave differently than the hydrogen molecule. It's going to behave differently than the singly ionized hydrogen molecule. And spectra like this, even with just a single atom, and this is just as predicted for the hydrogen atom with just a single electron, you already have very complicated behavior. So if I flip back to my motivating slide here, this is just looking at the visible portion of the hydrogen spectrum, and you can now identify this as the n equals 3 to 2 transition, this as the 4 to 2 transition, 5 to 2, 6 to 2, and if you continue into the UV, 7 to 2, 8 to 2, 9 to 2, 10 to 2, etc. These are the Balmer lines of hydrogen. When you work with more complicated atoms with more electrons, you have far more complicated behavior, and this is unfortunately something that quantum mechanics still really cannot predict well. To check your understanding of all of this, I have some simple calculations for you to do. First of all, figure out how the formulas that we gave for hydrogen would change for helium. You still have just singly ionized helium. So a single electron, instead of orbiting a single proton, orbiting an electron or orbiting an alpha particle, something with 2 protons. So the charge on the nucleus is going to double, and that will change the energies. Then make some calculations of energies, figure out whether they would be visible or not, and as finally, calculate the longest wavelength. Identify the transition for the longest wavelength in the Lyman series. These are conceptual sorts of questions that you need to understand the structure of the energy levels of hydrogen in order to answer, and there are also some simple calculations to do. But the fact that you are capable of making these calculations is really a triumph of quantum mechanics. We started with something that is essentially just an equation, hypothesized, almost entirely without justification. And it actually seems to work. You can do separation of variables, you can go through a lot of complicated mathematics, which from the physics perspective is more or less just turning the crank, trying to solve this equation. And the structure that you get, subject to all of this interpretation we did as far as the probabilistic interpretation of quantum mechanics requiring normalization of the wave function, and the overall structure of all of this leads to calculations of real measurable physical quantities. And for instance, the answer that you'll calculate for this is something that you can look up. If you look up helium spectrum in Google, you will get lots and lots of matches, and some of them will include data tables with hundreds, if not thousands, of observed and identified helium lines. And the energies that you calculate, the energy that you calculate will be in that list. And that's really quite astonishing if you think about it. It speaks to the overall power of quantum mechanics.